Chapter 7, problem number 46. It looks like this. Actually, it doesn't look like that. It looks, but the problem basically says a shot putter takes the shot put and throws it. And the final speed of the shot put 14 meters per second. And also during that time, they move the puck moves the putt shot put. It is a putt. Moves up zero point 0.8 meters. So like this, I guess. I don't know. I'm not a shot putter. And the question is, what's the power output of a human? So we actually have some work to do here, but not too much. They give us the mass, they give us the final speed, they give us the change in height, and they give us the time that takes 1.2 seconds. 1/1000. I guess that's okay. Okay, so let's calculate this. The very first thing that I'm going to do is I'm going to declare, and this is something that you should practice doing. We're using work as a change in energy. I want to find that work done by the shot putter. But to do that, I need to declare my system. Now, a lot of times people just skip over this, but it's important to say, am I going to do work done by gravity, or am I going to have gravity as part of my system? If I pick the putt, is that really what it's called? Plus the earth. Then that tells me what kinds of energy I can have. And in this case, I can have the energy will be kinetic energy plus gravitational potential energy. And kinetic energy we define as 1/2 mv squared, and the gravitational potential energy is mgy. So for the potential energy, we need to say where is y equal to 0, and there's no wrong answer. I should put it up here just to be funny, but let's just for now, let's put y is 0 down here, so y final is 0.8. Now I can apply the work energy principle. Work is going to be the change in energy, which is the change in kinetic energy, plus change in gravitational potential energy. And let's write that as K2 minus K1 plus U2 minus U1. Now, in kinematics, we use final velocity as V and the initial as V0 at time 0. But here we're not dealing with time, we're dealing with positions. The velocity at position 1, the velocity at position 2. So it's easier to go 1 and 2. I just want to point out the difference. Okay. So some of this stuff is 0. The final kinetic energy is not, but the initial kinetic energy is, right? Because it starts at rest. Also, the initial potential energy is at y equals 0, so the initial potential is also 0. So the work done is going to be K2 1/2 m v2 squared plus mgy2. Let's just go ahead and put a value for that. So this is going to be equal to 1/2, and this is the mass of the shot put. Technically the Earth could move too, and it does, but conserving momentum, the change in velocity and the energy of the Earth is negligible. And we'll look at that later. Okay. 1/2 m, the mass of the putt is 7.27. The final velocity is 14 squared. I'm going to put it right down here, plus 7.27 times g, 9.8, times the change in height of 0.8. Let's put that in our calculator. On drop. Okay, 0.5, 7.27 times 14 squared. The squared button's so small. Times, and then 7.27, enter, 9.8 times 0.8 times plus. I get 796.5. Let's go with that. 769.5 joules. So that's the work done. Now I want to calculate the power. So the power is defined as, I can erase all this stuff. Power is going to be the rate of change of energy, but in this case we're talking about the power of that person. So it's actually going to be the work divided by the time interval. So that's pretty easy. So it's just this work, 769.5 divided by 1.2 seconds. So that's going to be 1.2 divided by 641 watts. I should point out there's this really awesome graph of human power output as a function of time. And so over an extended period of time, like hours, most humans can do about 150 watts of exercise power output. Extreme athletes could do 300, 400 watts for a longer time. 600 watts is really, really, really high, but even you could probably do that. Imagine when you just jump, it takes a very, very short amount of time because delta T is very, very small. You can get very high power outputs, but you can't put that out for very long. Okay, the question also said, hey, convert this into horsepower. So I think, I forgot the conversion factor. 1 horsepower in watts. 735. That's weird. Okay, so let's convert this to horsepower. So the power is 641 watts. And then I can say that 1 horsepower is 735 watts. Is that right? I don't know. Sometimes, I'll tell you right now, sometimes I put stuff in Google and I get like an AI response and it's wrong. So I've done that before. I got like, but I think this one's, 746. See, 746. Some say 746. 746. Okay. I don't know where that. See? It's wrong. Okay, so I can just take that 746 divided by, and I get 0.85. And I read somewhere that a horse doesn't have a horsepower, but I can't remember where that came from. It's definitely an old unit of power. But I don't know, just convert it for fun, just in case you want to compare it to your car or something like that. So there you go. That's problem number 46, the end.